Hello there. In our attempt to determine the structure of a known organic compound, we have been able to use the degree of unsaturation to narrow down the list of possible structures. We have been able to use the infrared spectroscopy to determine the functional groups that could be present in the unknown organic structure. We have been able to use the mass spectrometry to determine the molecular weight and also to look at the fragments that could help us build the structure. However, all these details have not led us to a conclusive decision as to what the actual structure of the unknown compound is. So because of that, I'm going to introduce another strategy which is called the proton NMR. NMR stands for nuclear magnetic resonance. So molecules interact with the electromagnetic radiation, specifically in this case is the radio waves, where the atoms with odd protons or neutrons are known to exhibit a nuclear spin. The nuclear spin generates a magnetic moment similar to that of a bar magnet. So if we introduce an external magnetic field, then the magnetic moments of the nuclear spin will align themselves. And then when we expose it to radio waves of the right energy, the radio waves will disrupt that alignment and cause a realignment. As the realignment occurs, the nuclear spins will resonate at a specific frequency. And it is that frequency that we can be able to interpret by being translated into the NMR spectrum. So in the NMR spectrum, we have what is called the chemical shift. The chemical shift, like whatever I'm showing here, is ranging from 0 all the way to 14. That's what we are going to use mostly for this course. And then we also have the side, the higher side, we call it the low electron density region. That is the downfield. So protons that are found within this region do not have a lot of electrons that surround them, while the ones that are found in this other region have a lot of electrons that surround them. Look at an example of something like carboxylic acid, where we have the hydrogen connected to the oxygen. Oxygen is more electronegative. So this hydrogen here, this proton, the proton will be found at more downfield region because the oxygen actually pulls electrons from the hydrogen. If you look at something like a methyl group with a CH3, if you have a methyl group, then carbon is not electronegative and neither is these other hydrogen atoms. So each of these protons that will be analyzed will show up at a more upfield region because they are surrounded by more electrons within them. So, what structural information can we get from the NMR spectrum? When we look at the NMR spectrum, there are specific things we need to identify. We need to identify the number of signals, okay? So like here, we can identify 1, 2, 3, 4, 5. So we need to identify the number of signals in the spectrum. We need to identify the chemical shift, the location of the signal. So if there's a signal, we need to identify in which region is it. So this one is at around 8.2, roughly. Okay? This other one is at around maybe 3.8. Okay, so we need to identify where the chemical shift is. then we need to be able to do an integration or identify the integration. Integration is the area under the curve, the signal curve. So we can be able to calculate the area under this curve. Okay? The area under that curve will tell us how many protons are available within that peak. Then there's what we call the multiplicity or the splitting pattern. So these are the things we're going to look at one by one. So when we look at a structure, the signals will appear at specific regions, and we can determine the position of those protons, and that can help us build the structure of the unknown molecule. Let us start with looking at the NMR signals. To determine the number of signals, we need to visualize the actual structure and think of how it would definitely look like. Would you expect protons that are chemically equivalent to give different proton NMR signals? Well, the answer is no. Protons that are in the same chemical environment will give the same signals. How do we determine if protons are in the same chemical environment? We do that if, one, the protons are homotopic. That is, if there is an axis of rotation of symmetry in the molecule that allows us to interchange the protons. And when we interchange the protons, we don't see any difference. Then it means that they are actually in similar environment. For example, in this case, we can actually rotate this. We can rotate it, and we can call this proton A and B. When we rotate it, those protons will interchange, but we can't really tell the difference between A and B when we do that interchange. Same to here, so as long as there is an axis of rotational symmetry that allows us to interchange without seeing any difference, then we can be able to say that they are in the same chemical environment. Protons could also be enantiotopic. That is, if the molecule has a plane of reflection that makes one of the protons a mirror image of the other. So this one does not have an axis of rotational symmetry, but we can be able to interchange the protons so that one of them becomes a mirror image of the other. Okay, so when we do that, and one is going to look like it's an enantiomer of the other, so like a mirror image, then we can say that those two protons are enantiotopic. So in this case, this is enantiotopic, this is also enantiotopic if we change one proton with, say, deuterium, so that each of the groups in the stereocenter becomes different. We exchange one of them with the deuterium, and then we are able to identify one of them as a mirror image of the other. What if the protons are neither homotopic nor enantiotopic? Then what happens? Well, then that means they are not going to be chemically equivalent. If they are not chemically equivalent, we are going to have different signals. So for example, these two protons, we can have a plane of symmetry where we can rotate this molecule, and we're going to interchange those two protons. They are in the same chemical environment, so we're going to have one signal for those two. If we do the same with the molecule on the right, we do not have any axis of rotation. So therefore, these are not in the same chemical environment. So this proton and that proton are going to show different signals. Okay? So when that happens, we can say that, like in this case, we can say that these two protons are diastereotopic, because there's a chiral center and we don't have a plane of symmetry. So those two protons are said to be diastereotopic. Now I want you to classify the molecule here as being either enantiotopic, homotopic, or diastereotopic based on what we have just looked at. Here is some practice. Fill in the boxes to show the number of signals the compound will have in the proton NMR. So starting with the first one, which is a diethyl ether, we have these two carbon atoms being symmetrical and these other two also being symmetrical. So which means the protons bonded to those carbons are going to show similar signals. So we are only going to end up having two signals. If you look at the structure of hexane, again it has a line of symmetry, so we can end up with only three signals: HA, HB, HC. So HC, HB, HA. They are going to be symmetrical. If you look at the structure of benzene, again, all the protons around the benzene are going to be symmetrical. So we are only going to have one signal in the proton NMR. The ether here is also symmetrical, but because the connections are different, so if this is HA, it is going to be similar to that HA, and this is HB, it's going to be different. But whatever is on the right is going to be similar to whatever is on the left. So we end up with only two signals, the HAs and the HBs. Okay? Now let us look at any of these compounds that you think are going to be symmetrical. What you could see is we can have a line of symmetry here, or we could have it the other way. So when we do that, the protons that are in these compounds are going to be a reflection of each other. So in this case, we end up with just one signal. For the other cyclic compound here, what we can see is there is a possibility of having a line of symmetry around here. So therefore we have HA, HA, and then we can call this HB because it's going to be different, and HC is going to be different. So we have HA, B, and C, which gives us three signals. For this other compound here, the ester group, we have HA, HA, HB, HC, and then here we have HD. So four different signals. So usually you can look at a compound, analyze it, and determine the number of signals. So I want you to practice and make sure that you can verify how we are ending up with those signals by looking at the structure. So in the proton NMR, there is the chemical shift, which we talked about. Every proton is going to show up at a specific chemical shift in the proton NMR, depending on the shielding effect, whether it is downfield or upfield. That is, according to the electrons that are surrounding it. Now, the methyl groups will appear at around 0.9. If we have the methylene group, that is a CH2, hydrogen atoms connected to a carbon, which is connected to other carbons, so we're going to have that at 1.2, methylene group. If you have a methine group, where we have a tertiary carbon connected to a proton, that proton will appear at 1.7. If you have an allylic proton, roughly around 2, an alkenyl for a terminal alkyne is going to appear at around 2.5. For a aromatic compound, if we have what we'd call the benzylic position, so like in this case we have a methyl group, we're going to have the protons here appear at around 2.5. Now for the halogens, around 2 to 4, for alcohols 2 to 5, vinylic around between 5 to 6. Aryl group, when you have an aromatic compound, the protons will appear at around 6.5 to 8. For aldehyde, we're going to have them at approximately 10, and for carboxylic acid, the proton is going to be more downfield, so it's going to be at around 12. Okay? So again, these are estimates, but we are going to use them to guide us to determine the actual structure, as long as we know where the shift is showing up in the proton NMR. Next, we said we need to be able to determine the integration and interpret it accordingly. So in the spectrum, we will see these peaks, and then we can do the integration, which is the area under the curve. So we can calculate the area under that curve. When we calculate the area, that area tells us the number of protons, and specifically it gives us the ratio, so that when we look at the whole molecule, then we can look at the spectrum, and the spectrum will tell us the ratio of protons within the spectrum. So here we have 3 protons, here we have 2, here we have 3, here we have 2. When we have the decimal places, we round them up to the nearest whole number, because we cannot have half of a proton. So usually we have to round them up to the nearest whole number and use the number of protons to kind of generate a ratio that represents the actual position of the electrons and how many of them are in those positions. The next thing we look at is the multiplicity. So the integration tells us how many protons are in each signal, okay? The multiplicity tells us how many protons are neighboring the actual proton we are talking about, okay? So when you talk of multiplicity, we mean the splitting. Equivalent protons do not split each other. If they are in the same chemical environment, no splitting. So we can have a singlet. Singlet means that it's just one peak, not split. A duplet means it has been split into 2, triplet for being split into 3, quartet for being split into 4, quintet for 5, into 6, and into 7. Okay? So it is the neighboring proton that splits the proton that is adjacent to it. It needs to be adjacent, so it has to be within 2 to 3 bonds in terms of the distance. For example, this is 1 bond away, then another bond. So this is 2 bonds away. If these 2 protons are in different environment, they are going to split each other. Okay? This is 1 bond, 2 bonds, 3 bonds. So if HA here and HB are in different environments, they are going to split each other. However, if they are too far apart, they cannot split each other. So HA is 1, 2, 3, 4, 5 bonds away. If it is more than 2 or 3 bonds away, well, more than 3 bonds away, then they cannot split each other. Okay, so no splitting is observed if they are more than 3 bonds away. So keep that in mind. Then there's a rule we do follow. We call it the N+1 rule of or where N refers to the equivalent protons on the adjacent carbon. So what happens is, let us look at this structure over here. In this case, we know that there are 3 protons, and then there are 2 protons on this one, and we have 3 protons over here. So let us first of all find out how many signals we are going to have for this compound in the NMR spectrum. So we have HA, AA, HB, and then HC. So we're going to have a total of 3 signals, okay? Splitting only occurs when a proton is connected to a carbon and another carbon. So no splitting occurs if you have oxygen connected to a proton. It only occurs if you have carbon connected to that, and there's another carbon which is also connected to another proton, okay? So in this case, there is going to be no splitting for HC. So HCs are going to show up as one signal which is not split. And it's going to show up as the one that you see over here. So that's going to be for the HC signal. Let us look at the HB. So this proton here is connected to a carbon which is connected to another carbon which is connected to the HAs. So that is 1, 2, 3. 3 bonds away, so splitting can occur. So according to the N+1 rule, if we are looking at the HB, HB is going to be split 1, 2, 3. We count the 3 protons that are adjacent to the carbon that is attached to the proton we are looking at, HB. It's going to be split 4 times. We use N+1 rule where N is the equivalent protons on the adjacent carbons. Okay? So it's going to be split 4 times. So we just need to look at it and see which one is split 4 times. So this is going to be the HB. How about HA? HA is going to be split. We have 2 protons here, so 2 plus 1. So HA is going to be split 3 times. So we're going to have 3 splits. We call that multiplicity. So it's going to be a triplet, okay? So here we have a triplet. Here we have a quartet, and in this case we have a singlet, okay? So that is how we play around with multiplicity. So multiplicity actually tells us the number of adjacent protons. Isn't that cool? There are some signatures that we can use to help us depict how many protons are there in a very easy way. For example, the tert butyl groups, anytime you see 9 protons that show up as a singlet, then that means we have a tert butyl group. Right? So keep that in mind. Anytime we see 9 protons showing up as a singlet, that's a signature peak for a tert butyl group. If we do have an isolated isopropyl group that is isolated, then we can have 6 protons. Okay? If there's a proton there, so this proton is going to show up as a multiplet. Septet to be specific, because we have 3 protons plus 3 then we employ the n+1 rule. So this proton is going to be split 7 times. So we have a septet, but it is only one proton, so the integration is 1, but it's split 7 times. Then each of these 6 protons, they're going to show up here, but it's adjacent to just one proton. So according to the n+1 rule, this is going to be split only 2 times. So we have a doublet. Okay? Why is splitting not observed for some protons? Well, splitting only occurs for protons bonded to carbons, not oxygen, not nitrogen. Okay? In fact, in some cases, the signals may not even appear in the proton NMR, especially so for protons that are bonded to more electronegative atoms like oxygen or nitrogen, which implies that these compounds are likely to participate in hydrogen bonding. So if you use a deuterated solvent like deuterated water, now NMR is usually performed in the presence of deuterated solvents. So it could be deuterated chloroform or deuterated water. So if you use deuterated water, then deuterium is going to exchange with the proton if there's a possibility of hydrogen bonding, which therefore means the electronegative atom is going to be able to release this proton, leading to an exchange. So if that happens, we are not even going to be able to visualize the proton that is closest to nitrogen, and they will not even show up in the proton NMR. Let us do a little bit of exercise. Predict the splitting patterns for all protons in this molecule. The first thing we need to do is to determine how many signals are going to be there. And in this case, we have a proton here, we call it HA, HB. They are not equivalent because we don't see any symmetry in this molecule. Then we have HCs, where we can rotate this bond. When you rotate this bond, we can interchange HCs and they are going to be the same. Then we have HD, then HE, and then we have HF. Okay? So for these compounds, we can be able to determine the splitting pattern. For HAs, we're going to have each of them being a duplet because they are splitting each other. For HC, it is closer to HD. So because HC is closer to HD, the HCs are going to be a doublet. They're only going to be split into 2 because there's only one proton closer there. For HD, there are 6 protons on the adjacent. There is an adjacent one on this other side and then another one on this other side. So there are 6 protons, so it's going to be a septet. For HE, if you look at the adjacent one, we can see HFs. There are 2 of them, so that's going to be a triplet. And then for the HFs, the adjacent one is HE, so we're going to have a doublet. Okay. We can also look at the carbon NMR exactly in the same way, also the splitting pattern, but we don't look at how many adjacent carbon atoms are closer to it. Okay. So what we do is we just look at the position with respect to the functional groups. So the general idea here that I want you to be able to understand is the position where it comes. So in the carbon NMR spectrum, the chemical shift ranges from 0, we're going to have it all the way to 120 for the purposes of this class. So all the way from 0 to 220. Now, if we have single carbon-carbon bonds, the single carbon bonds are going to show up between 0 and around 90. That's all I want you to know, between 0 and around 90. If we have a triple bond, the triple bond is going to show up within around 50 to 90. So again, all I want you to know is that the single bonds, the sigma bonds are going to show up between 0 to 90, and also the sp hybridized carbons, that is the triple bonds, are also going to show up at that region. Then the alkenes and the aromatic compounds, those carbon atoms will show up between 100 and 150. And then from 150 to 200, we're going to have the carbonyls. They could be ketones, they could be aldehydes, they could be carboxylic acids. So the carbonyls are going to show up at between 150 to 220. That's the general idea that I want you to know for the carbon NMR. Here is a summary of the chemical shifts in the NMR spectra. So for proton NMR, you need to be able to identify where the proton is attached to. If it's attached to an aromatic compound, we say roughly around 2.5. If it is a terminal alkyne, then the proton will appear at around 2.5 to 3. Okay? And for carbon NMR, what I said is you need to be able to identify the single bonds and the triple bonds appear below 100. From 100 to 150 is where we're going to have mostly the aromatic compounds and the alkenes. And then the carbonyl functional groups will appear usually at around 180 onwards. Okay? Predict the structure of C5H12O, given that these are the possible structures that could match the spectra. So this is a proton NMR, and we only have 2 signals from what we have been shown. So that means we are going to look for a compound that will give us only 2 signals. Of course, the alcohol is out because that's going to give us many signals. This is also out because we're going to have many signals, more than 2. This is also out because we're going to have HA, HB, HC, HD. So the only one is the one that contains a tert butyl group. So the other good thing is a tert butyl group gives us 9 protons. So we see a situation where we have 3, 3, 3, 3. So the ratio is 3:9, which is 1:3. So 3:9. So we can look at the ratio of that signal to the one of that signal, which is 1:3. Predict the structure of C8H10. There are only 2 signals, and they are all singlets. Wow. So we are looking for symmetry here, where there is not going to be any splitting pattern. Okay, so obviously it's not going to be the first one, because then we're going to have HA, HB, HC, which is supposed to be 3 signals. Again, it's not going to be this one, because that's going to give us also more than 2 signals. And if we look at this one here, we're going to have HA, HB, which is going to be similar to that. And of course, that HB is similar to the same HB on either side. So we end up with only 2 signals. So this is the right one. Okay. If we look at this other one here, there is no symmetry, so we're going to have more than 2 signals here. Now let us analyze the one that we circled and see what happens. So we have aromatic compounds. Aromatic compound will have the protons, so HBs. HBs will appear between 6.5 all the way to 9. Okay, so anytime you see protons between 6.5 to 9, then they must be aromatic protons. And here we have 4 of them, so this is supposed to have an integration of 4. And then we have, this is going to be 3 protons, so we have 6. So this one is supposed to have an integration of 6. Okay, so the ratio is going to be 2:3. And you can see how that ratio matches exactly what we have for the compound. Predict the structure of C3H6O2. And we're given the list of possible structures. We just need to find out which one matches the spectrum. And here we have the signals appearing at position 2, and the other one is at around 3.7 in terms of the chemical shift. And there are only 2 signals. So let us see what happens. Starting from the right, this could be HA. Then we could have the protons in that position as HB and HC. So that is out because it's going to give us 3 signals. Here we're going to have HA and HB. So that's going to give us 2 signals, and HC. Of course, this is not going to be split, so then that is not right. Let us verify if indeed we do have the one on the left as the right one, or maybe we don't have any of them matching. So let's find out. So this is going to be HA, and then we have HB, and this HA is closer to oxygen, so that means it's going to be more deshielded. It's going to be more downfield. Okay, so that is this is going to be 3 protons over here and 3 protons over here. So the HB is the one that's going to be here, and the HA is the one that's going to be here. Predict the structure of C6H12O2. So we're given the spectrum and a list of possible structures. Now, starting from the extreme right, this is going to give us HA, HB, then HC. So we're going to have 3 signals, so that is out because we only have 2 signals. So this is going to give us 9 protons, and that is 3 protons with the 2 signals. This is going to give us 3, this is 9. So we get 2 signals for each of them. The only difference we can be able to see here is that this proton, let's call this HA, and this one's HB. The HA is connected to a carbonyl, while here, let's call that HA prime. HA prime is connected to an oxygen. Okay? The one connected to an oxygen is going to be more downfield because it is deshielded. Okay? So therefore, we are going to experience this one more on the downfield than the one we have here. So let us see what happens. We know that this proton should appear at around 2 point something, 2.3, 2.4, 2.5, whatever it is. And then we have this one here, connected to an oxygen, should appear at around 3 point something. So therefore, the actual structure is this one. due to the position of the methyl group attached to the oxygen. So it gives us the right compound with a ratio of 3:9. Determine the structure for C4H9Cl given the proton NMR to be of chemical shift 1.68 singlet with 9 protons. So here we now have to figure out what the structure is. 9 protons, we said, means that we have a tert butyl group, and this compound has only 4 carbon atoms. So we have 1, 2, 3, and 4. So CH3, CH3, CH3. That's 4 carbon atoms, and we could have chlorine over there. So that means we are going to have 9 protons, no splitting. So we end up with 9 protons, no splitting. Integration is 9. Determine the structure for C4H9Cl given the chemical shifts in the proton NMR to be at 0.96 we have 3 protons. So at 0.96 means that we are likely to have a CH3 because it is more on the shielded side. So the methyl or the ethyl groups, those ones will appear closer to 0. And we have 4 carbon atoms, so we have 3, we have catered for that. Then we have, now this is a triplet. So that makes sense because we have 2 protons here, which makes it a triplet. But these 2 protons are going to have a quartet if they're close to that proton. So we need to be able to see a quartet or more. If indeed there are some protons here, then the splitting pattern for these ones is going to be 3 plus that is 5. So we're going to have 6 splitting patterns. Okay, let us see if we have, well, we do have a multiplet. So that means we indeed have something like that. CH3, then these 2 protons over here. Then we have those 2 protons. So we have a multiplet, and then we have another 2 protons. And then we have a Cl. So 1, 2, 3, 4. So 2, 2, 2, 2. 2, 2, 2. And then we have 3 protons. So the structure for this compound is going to be CH3, Cn. 1, 2, 3, 4. Okay? And you can monitor the nice splitting patterns that are shown here for each level. Predict the structure of C4H9Cl given the proton NMR with chemical shifts. 6 protons at position 1. That is going to be an isopropyl group. So we just draw that isopropyl, 3 protons, 3 protons. And if there's a proton here, that proton is going to be a multiplet. And that's what we see here. So that means our isopropyl and the one that's going to have a septet makes sense. And then we are told there is 2 protons at 3.41. And those 2 protons are duplets. That means we are going to have those 2 protons over here. And those 2 protons are attached to a carbon which is connected to a proton, just 1 proton. So there's going to be a duplet. And then we have chlorine. So the structure is going to look like this. Chlorine attached to a carbon which is attached to the isopropyl group. Predict the structure of C11H14O given the proton, NMR, and an IR. Wow. Okay, so let us try to put everything together so we can find what the product or what the structure is going to look like. So we have 6 protons, which tells us that we have an isopropyl group. Then we have a multiplet, so we can simply say there's a proton there. So this is 3 protons connected to that. And we have a singlet at 3.41, and then we have 7.24. That means we do have an aromatic compound. So the first thing we need to do is to sketch it. And the aromatic compound has 5 protons. So that aromatic compound is attached to another group. So we have accounted for the 5 protons gone. We know that there is an isopropyl group. There's also an oxygen that we need to account for. So do we have a carbonyl or not? We need an IR to help us with that, and that means we have a carbonyl. So if there's a carbonyl, let's try to see what happens in terms of the splitting pattern. We have accounted for that one. We have accounted for this proton because it is split. We have a singlet at 3.4. Singlet at 3.4. So that means at 3.4, this compound could have the 2 protons being here and there, and then we have a carbonyl over here, and then we have this other group, CH3, and okay, and then there's a proton over here. Okay, so we have accounted for this one. This proton is supposed to be split 7 times. That's the multiplet we have over there, which makes sense. These protons are not supposed to be split because there's no adjacent proton here, there's no adjacent proton there. So it's going to be a singlet. And that helped us to determine the structure of the compound. So the compound looks like this. That is the structure of the compound. Determine the structure of C5H10O. What do we have? What we know is that there's going to be a carbonyl because we have a strong peak at 1725. So we are sure of a carbonyl. Then we have a proton NMR. 9 means we do have a tert-butyl, 3 protons in each of them, and that's supposed to be a singlet, which means there's no adjacent, obviously there's going to be no adjacent proton because it is a singlet for a tert-butyl group. Then we have at 9.52 a singlet of 1 proton. Usually at around 10, that's where you find an aldehyde. So we know that there's an aldehyde. Any other information we know? Let us see. So an aldehyde is accompanied by a carbon NMR that appears at around 206, a signal for an aldehyde. Remember we said carbonyls, like an aldehyde, a ketone, or it could be an amide or carboxylic acid. Those carbonyls will appear at around 180 to 220. Here we have a variety of stuff. We don't really need to care much about that. I just told you guys that for sigma single bonds, we will have them at between 0 to 90, or about below 100, including the triple bonds. Okay. So all we know from here is that we have the 4 carbon atoms and the 5 carbon atoms. So we got it. All we need to do is put it together. So we have that connected to a hydrogen, connected to that. That gives us the correct structure. Provide the structure of C4H8O2. And what we have is a singlet having 8 protons, which appears at 3.64. So this compound must be symmetrical. That's the only way we can have 8 protons appearing as a singlet. So the possibilities could be 1, 2, oxygen connected to oxygen. Is that a possibility? Probably. Then we could have 3, 2, 3, 2. How many protons in total? That's going to give us 10 protons. So this is not right because that gives us 10 protons. So we can calculate the degree of unsaturation, which is going to be 4 times 2 is 8, plus 2 is 10, minus 8 all over 2, which is going to give us 2 divided by 2, which is 1. So there's 1 degree of unsaturation, which means there must be a double bond. And this compound is having 2 oxygen atoms, and it is also symmetrical. So we could think of a cyclic structure. We could have something like that. Oxygen. That gives us 4 carbon atoms that are symmetrical. And that's going to give us only 1 peak, because if we do that, this peak is symmetrical to that peak is symmetrical to that, so we end up with only 1 peak. And that is going to be the actual structure with 1 degree of unsaturation and being symmetrical. Predict the structure of C5H11Cl given the proton NMR to be of chemical shifts 0.96 with 3 protons, 1.53 with 2 protons. So we have 2 protons, 3 and 6. Anytime we have 6 protons, we could think of an isopropyl group. This is a chlorine. Now this is a singlet. The fact that it's a singlet means there's no proton in that position. So we could simply say that what we have is chlorine attached over there. That's the only way we can have those 6 protons being a singlet, if there's no proton in that position, and then we can have a carbon attached to something else. So we have 2. Let us look at the 2, assuming there are 2 protons here. Let us look at what's going to happen. To these 2 could be attached to these other 3 protons. Well, adjacent to these other 3 protons. So because they're going to be adjacent, that means these 2 protons are going to be split 4 times, n plus 1 rule. So because they're going to be split, predict the structure of C5H11Cl given the proton NMR with chemical shifts, 0.96 being a triplet with 3 protons, 1.53 being a quartet with 2 protons, and 1.64 being a singlet with 6 protons. That's a signature for isopropyl. So that means we have that group, but it's a singlet, which means there's no proton in that position. So we could say that it is like this and could be attached to a chlorine, so that there's no proton in that position. So we have 3, 3, 6 protons. We have accounted for that. We have 2 protons that are going to be a quartet. So we could have it like that. So the 3 protons here and the 2 protons here, these 2 protons are going to be split 4 times, a quartet. We have catered for that. Looks good. Then we have these 3 protons are going to be split 3 times due to the n plus 1 rule. So we've accounted for that, and the actual structure is and that brings us to the end of these practice exercises. Have a good one, and let me know if you have any questions.